Today we'll be completing lesson 5.2, which is analyzing exponential function. The first lesson we looked at sketching exponential function. The subsequent lesson we looked at transformation of exponential function. And today we'll finish it off by looking at different methods of sketching graphs of transformation of exponential function, but also using transformation of exponential function to model real-world situations. So we'll look at one example where you'll be using exponential function transformation to model real-world situation. Just to recap, we said that the exponential function is any function that can be written in the form y is equal to a to the x, where a is positive, and we have two sketches here to demonstrate the increasing exponential function and decreasing exponential function. And we've done a fair amount of sketches. Then we looked at transformation, and this is what we've been doing the past lesson, or what we did in the past lesson, that if you have a graph y equal to x, the equation of its image is y minus k, which is a vertical translation, the vertical shift up or down. Then we have a horizontal shift c, which is your compression, and that is your vertical compression, is your c, by a factor of c. A. Now d is your horizontal stretch or compression. If it's a fraction here, it means there is a stretch. If it's a whole number, it will be a compression. H refers to the horizontal translation. Notice A has to be greater than 0. And we also discovered that the general transformation, if you have y equal a to the x and the y, that the x and the y could be transformed. The x in the transformed form would be x over d. So we find our d value here, plus h, which is the horizontal translation. And the y for the translated corresponding xy value for a to the x. This is your y, this would be your new x. For the transformed one would be cy plus k. So that's what we did yesterday. And in one of the questions we did yesterday was question 10. I just want to recap what we did in question 10. In question 10, I showed you when you're given when I ask you to sketch the transformation of a function, we go back to the original a to the x graph or function from this transform there. And we can find that by stripping away any transformation from it. Here is your vertical translation, and this is your horizontal compression. If we remove these two, we're left with y is equal to 2 to the x. And that is this graph here. And I showed you how you can use the general transformation. And then I use the general transformation, which is xy, x over d plus h, cy plus k, to find the coordinate points for the transformed exponential function, which was a lot of work. First, I need to find my x and y. So I sketch my a to the x graph, which is in this case 2 to the x. Then I use the coordinates for the 2 to the x graph and substitute the values into the transform to the corresponding transform x and y to arrive at the coordinates for the new transformed x and y coordinates. Today, what I'll show you, I'll bypass y equal 2 to the x. I'll do the same graph, and I wouldn't use the transform corresponding transformation, but I'll use the exact values from here. Let's look at what I'm referring to. So I'll keep this aside here, but here, an exact question I'll be going through. Okay. So here's my question. Just ignore, just imagine we ignore what we did earlier. Then we go straight into, we have y is equal to 2 to the power x plus 1. So we have a vertical translation, meaning 1 unit up. And we have a horizontal compression of a half. So there's no horizontal translation. So this would be your normal graph if it would be going up this way here in terms of y equal to a to the x. But now this shifted up 1 unit. So now this will become my new horizontal asymptote. Y is equal to 1 because it shifted 1 unit up. So normally it'd be here shifted 1 unit up. Now, what happens to this graph because we have a compression of horizontal compression of a half. Now, I'm going to use the exact to find the value for the y. I'll select any value for x. And the y coordinate for the transform function, I'll find it by substitute the value I selected for x into the y to give me my y values. So I wrote it here. So I strip away the y because 1 plus. Now, to make my calculation much easier to follow, this is 2 to the power 2x plus 1. I simply put a 1 in front of it. So it becomes add 1 plus 2 to the power 2x. Just to make a change of form. If you're happy with it as it is here, that's okay. You could have written this as 2 to the power 2x plus 1. You'll have the same result. I just changed it to make it look much easier to follow. So now I have 1 plus 2 to the power negative 1 here, which gives me 1 plus 2 to the negative 2, which is equal to 1 plus 1 over 4. So my coordinates would be, now if I were to put a line through here, so this is my new x and y for my transform function, would be negative 1, 1.25. Now, if you go back to what we did earlier with the other one, we also get the same result. Okay. You'll find out which one is easier. There are some drawbacks to this one here, but if they just ask you to sketch the transform function, you can go straight into this method. So let's look at this point here. It is negative 1, 1.25, negative 1, 1.25, which is here. You know if you're in the wrong path, if this would have been below it. And this we know is positive. There's no reflection. The next we have 1 plus 2, 2 to the power 2 times 0, which gives me 1 plus 2 to the power 0, which is to the power of 0 is 1. 1 plus 1 equals 2. So this is my, so 0, 2, and that makes sense because that becomes my new y-intercept. So I can connect these points here. So I know this graph is going down this way. Now 1 plus 2 to the power 2 times 1 gives me 1 plus 2 to the power 2, which is 1 plus 4, 5. So this is my 5 here, 1, 5. So 1, 5 is up here, continue this point. And we'll just do one more to make sure we're getting the right trend here. 2 times 2, which is 1 plus 2 to the power 4, which is 1 plus 16, which is 17. Now this is way above, way beyond my scale. It's way up here, so let's continue this here. Now that's much quicker than what we did with this previous one here. But in this question here, they ask you to go back and sketch a graph to the original graph, the non-transformed one. And here we discovered that our asymptote is still, so we have our is 1. So the domain is x set of real numbers, and the range y is greater than 1 because it's above. The asymptote is y equal 1. The intercepts, we know it's here is 0, 2. Y-intercept is at 2, or we can say it's 0, 2. And the function is increasing. Because as x increases, y increases. Now, let's go on to the next question. Now, I hope you can see this, but this is a negative 2. I'll just write it a little bit brighter, so hopefully you can see this. This is question 10b in your textbook. Thought it was a good example, which is y is equal to negative 2, 0.5 x plus 3. Now, I've already, to expedite things here, I've already created a grid. And this would be my new x and y. I've created a grid. And notice I've 0.5 x plus 3. So it looks much clearer. I selected a few values for my x coordinate, and this is where the trickier part can come in. If I were just selected negative 2 to negative to positive 2, oops, this should be 1 here. Should it be 1? You'll notice that you may not get the right shape or the trend. It's very difficult to find. So that's where this may have some drawbacks. But I'll show you how to fix that. Now, to find my y, so now I have a negative 5 here. I'll choose negative 5. Now I need to find my y value, y coordinates. Now, notice what I did here. I isolated negative 1. So there's a negative 1 in front here. So I isolated it to make my calculation much easier to follow. the negative, this is, it's not a -2, it's actually -1 in front of it. And the 2, so if I were to isolate this, this is what it's supposed to be like. These are all together. So that is why I isolated -1. So we have -1, 2.5. We have x here is -5. So we have -5 plus 3. Work this out as -1 of 2.5. -5 times plus 3 is -2. Which gives me -1 times 2, -1. Because -2 times 0.5 is -1. Which works out to be -0.5. So this is -0.5 here. So be careful with this here, just to show you. Here we have -1. Let's put it aside here. I'm going to let's just show you what, just in case we have -1. We have 2, we have 1. So rewrite that. -1, 2 to the -1 becomes -1, 1 to 2. So this becomes -0.5. Just so if you're wondering how I got that. Now, our next step is to continue. Here we have -1, 2.5. Here we have -3 plus 3. It will give us 0. So we have here -1.5 times 0 will give us 0. So we have -1, 2 to the power 0, which is 1. So we have -1 times 1. So we have -3 here. Negative times 1 times -1. So first point is color point first here. So we have -5, -0.5, which is about there. We have -3, -1. It's right here. Notice this is a reflection. There is no vertical translation. So your asymptote will be right on the x-axis. Well, it's y equals 0. If this graph wasn't reflected, then it will be going, there will be a horizontal shift to the left, 3 units, 1, 2, 3. It will be, this point here is going up. If we were to do the ones without a reflection. This graph is reflected, so it's going to be going downwards. Let's see if that's the case. Now we have -1, 2.5. And here we have -1 plus 3, which is -1, 2.5 times 2, because -1 plus 3. So we result into -1. Now 2 times 0.5, will give us 1. So -1 times 2 will give us -2. So this is -1 here. So -1, -2. So let's connect. Go to 0, 2.5. I'm using same function. What would y is equal to? We have 0 plus 3. -1, 2. We have 0.5 times 3, which will give us 1.5. Which is -1. Now, approximately, it's going to give us, if you were to work this out, to be -2.2. I worked it out. Let's see, that'll be what? Let's see what calculate. What would that give us? 2 to the power 1.5, 2.83. So we have 0, -2.83. So 0, -2 about here. Connect that point. Let's look at one final point. -1, 2.5. We have 1 plus 3 is 4. So we have -1. 0.5 times 4 will give us 2. So this is 4, -4. So 1, -4. This graph will continue. And there's our sketch. The question asked now, the function is increasing or decreasing? It is decreasing. It's going to, as x increases, y decreases. So number 1, I, decreasing. As x increases, y decreases. Let's put it here, y decreases. Next, I ask you the intercept. Now, there's no x-intercept. But there's a y-intercept approximately where it's -2.38, y-intercept at approximately -2.83. Equation of the asymptote, y equals 0. And we have a domain and range. Let's be 3 here, be 4. Domain, x set of real numbers. And the range, now the range, it's below the x-axis, so the asymptote is y equals 0. So we can say the range, y is less than 0. So to recap, anytime you're asked to use transformation to sketch a graph, we could use our general transformation, or we can select any x values from, and then using our function given, find the y values and sketch your graph. You have to be careful regarding your vertical translation. If you don't get it right, you may end up sketching the wrong graph. But this works remarkably well. It's much straightforward. It's less work. So if you want to try this method, or the method we tried earlier regarding sketching graphs, it's fine. Go ahead. Now the last part we'll look at, we're going to look at one final question where we are going to use transformation of exponential function to model real-world situation. And the example I'll be looking at is example 3. Now you may use decimals in this case here, but I'll use the graphing calculator. So here we have the growth of the internet can be measured by the number of computers offering information. These are called hosts. In 1995, there were about 7.4 million hosts. Now, the numbers are astronomical today, but this was almost the infancy of the internet. So 7.5 million hosts. The number of hosts in n millions at any time t years after 1995 can be modeled by the function n equals 7.4, 1.59 to the power t. T is for time. N is the number of hosts in millions, by the way. So we're looking at millions here. The year we're starting off is 1995. So if you were to sketch, give a sketch, we're going to graph the function. So we'll have a function that basically, oops, that's all right here. We'll do a sketch. Now, since this is all positive, we will not go into negative realm. We'll have here in time. And 0 is the year 1995. And on our y-axis, I'm going to remove this because we don't need it. Yes, we can go back to negative host. Not in this realm here. So time in years. So we have here time in the year. So we have 1995 going this way. Now, this is the number of hosts. And this will be in the millions. This is initial amount, so this would be 7.4 right here, 7.4 million. It's an exponential function. This is how many times, 1.5 times it is increasing each year. And that's your time. So I'll use my graphing calculator to graph this function. So we know it's an exponential function. Let's go to my calculator here. I'm going to go into my y equal button. Now I'm going to remove, oops. So, okay, so go back to it. Now I'm going to input into my calculator. And you can use decimals for this. This will be my y. That will be my x in my calculator. So y1. So if I could transfer that, y is equal to 7.4, 1.59 to the x. So my calculator will follow through with this. Okay, let's go this here. 7.4 bracket. So this will be the initial amount. We start with 7.4 million hosts. 1.59 to the power x, this bracket. for the graph. And now I have set up my X and Y axis. Now this is my years. So I'm going to shut my window. I'm going to go up to 25 years from 1995. So I have up to 2020, up to this year here. So the 2020 is from 1995. So I'll set my calculator, remove 0. Now, the number of hosts here is huge. So I'm going to reset my window. Like, maybe to show you how it would appear, maybe 20 here. And you notice that would be 7.4 million, because this is my, what? I don't need my negative y values either. So I'm going to remove, I think that's 0. So here is 7.4 million. That's my initial point. Now, 7.4 million, it'd be a huge number. So I'll change my y coordinate to maybe, instead of being 20, I'll make that 1,000. So you'll see the trend much better. So this would be a 20-year or 25-year trend. So you can see it. Now, so that's my sketch, my graph. I will be going up like this. 7.4, 1.59 to the power x. Now, to the nearest million, estimated number of hosts 2010. Now, 2010, now in my graph, go back here, this is 0 here, 2010. So if I go up an increment of 5, so 2000 would be here. Would be 1 would be 2000. 2 would be 2005. 3 would be 2010. So what is my y value when x is 3 in my case here? Because 1995 is 0. This would be 2000, 2005, 2010. It asks me in 2010. So I'll go to my calculator x and I'll find when the value in x is 3, y is that wonderful number there. Okay. Now that will give us in 2010. Oh, sorry, this would be only 3 would be 15 years. Oh. So yeah, 5, 10. I got that wrong. Correction. Be 15 years. Looking at 15 years. Now that makes sense. Because I was looking at 1 times 5 years. So in my calculator, it's actually 1 means 1 year. So it will be 15. So when x is 15, because it's 15 added to 1985, give me 2010. So this is 2010. When x is 15, y, my calculator is 7,765.84 million hosts. So for B, it says here, in 2010, there were 7,765.84, and this could be a million hosts. Which is a huge number, I can imagine. And that's not surprising. The internet has grown tremendously. Now, the next question is in what year did the number of hosts reach 100 million? So in other words, when y is 100 million, So if you would write this here, when y is equal to 100 million, so 1,000 million, what is a year? So in other words, what is x? So because we're looking at the x value here. So what is x? Now to do that in the calculator, it's a little bit more here. So I go to my calculator here. Now I already have my graph. Now I'm going to go to my graph in my y equal button, and I'm going to go into one and make this 1,000. So now that is way above here. So now I need to increase my window so I can see more of that. I will make that maybe 1,200. Now I probably, well, there we go. Takes a while. I thought it wasn't working. So at this point here, this line represents y at 1,000. So I need to find my x corresponding value of x here. To do that, I'll find where this point, where this the line here intersect our function. To do that, I'm going to press second trace intersect, and I hit this 3 times, and that will give me, when y is 1,000, the year will be 10.57 years from 1995. So x is equal to 10.5, well, approximately, which is a years, so 10.58 years. After 1995. So if we add 1995 to this, will give us what? 2006 approximately, so it will be in the year 2006. Number of hosts will, or in this case, we're looking back in time, will be, or we say number of hosts, we should say was, yes, because we are now in the past tense. In 1,000 million. For these questions, the calculator will make it easier, but you can still use your, I can simply go ahead and put my years in here to find number of millions. You could have done it the other way around. To find x, you're given n, but also in the first case here, they give you how many hosts in the year 2010. You could have, in this case, put x equals, in this case, we're looking at 15 years. So 15, and we'll have the same result. So let's try that method. Let's see if we get the same result. So using the algebraic way, so y is equal to 7.4, or say n. We're looking at b in millions. So n, 7.4, 1.59, and ask us in 2010, which is 15 years. So the year would be 15. And remember, this is going to be number of millions. So we go to our calculator, home button, clear. So we have 7.4 in bracket 1.59 to the power 15. And we have the same result. So we can do it without a graphic calculator. So an answer will be 765.84 million hosts. Finding for x now, we can find for x. We could do that algebraically. In this case, n is 100, 1,000, 7.4, 1.59 to the x. Now, I'll leave this here for now, because in our next lesson, we'll be working on this question here to find how we can find x. I will solve that. I will show you that today. I'll leave that for our next lesson because it's more related to lesson 5.3. So to recap, today we looked at a different way of sketching or finding the coordinates of exponential, transformation of exponential function. We select x values and then we use our function to find the corresponding y values. And we sketch a graph for both of these. Then we looked at using transformation of exponential function to model real world situation. And we're using the graphing calculator, but also we can use the algebraic way of doing it.